So we're a company that's been around for 15 years, a little bit more, 17 in fact. Still pretty small, so 500 people. That's kind of a good thing. That means you can talk to real people who do stuff rather than having this big barrier of this big layer in front of you. We develop, build, install, support storage systems for usually the higher echelons of I/O and storage problems. Whether higher echelon means capacity or performance or distribution, we try and meet that demand at the very high end. We do have a European tinge to us now, quite a strong tinge, in that we're based in the US. It's kind of Silicon Valley-ish company. I'm currently in Chatsworth, but we have a large and growing development site in Paris, in the South Paris and Moudon. And that's in fact where the developers of IME sit. And IME is really the main topic for this talk. So in fact, the kind of overall theme of this talk is this one. We've got an application and it's got certain characteristics which make it very good for exactly what it does. It swims about in the water, it eats little grubs and I don't know what they eat, weed. It floats very nicely, it can fly occasionally when it wants to, so everything is perfect. It's taken 1 million years to develop, and it's very, very difficult to change that duck. And what we want to do is this, take the same duck and somehow make it go faster. And that's really the summary of the talk. So what are the I/O challenges? I won't go through each one, but we've already seen that we're in this new environment of larger concurrency, so higher thread counts, and that's driven not just by CPUs going from 16 cores to 32 cores, or whatever, it's by GPUs coming in and vastly exploding that kind of CPU count at the back end. Our applications are becoming more complex, multi-physics, adaptive mesh refinement, all this stuff, while you probably as application developers, who's an application developer here of some sort, or used to be, let's say used to be. The fair people, or in charge of application developers. So all these things, while you think of them as being compute stuff, adaptive mesh refinement, multi-physics, complex workflows, that all has a big impact on the I/O patterns. And many of these can be problematic for file systems today. So this kind of table shows you the kind of trends on the left-hand side, the character of the I/O that results from those trends, and the problems that usually causes when you present even a good, expensive, high-end parallel file system with these kind of workloads. And the parallel file systems can kind of limit your application performance through file locking, if you're doing shared file I/O. It can do it through disk thrashing, because you've got hard drives behind there, right? So if they get confused by many, many I/Os, they're going to go slower. We can confuse the caches and not really allow all that wonderful software technology to accelerate an application through caches, because we're just presenting random I/O. So many ways we can cause our application unwittingly to perform very badly when it comes to I/O. More animals, just keep you alive. So here's what we actually do day to day at DDN. We've been doing this for 15 years. Customers come to us and says, please can you give us a 30 gigabyte a second parallel file system? And we'll give them a parallel file system. We'll run an IOR benchmark, a sequential streaming throughput benchmark, very perfect. We tie the threads to the right cores, we pin them to the local memory and the I/O card, and we stream that I/O distributed perfectly across a Lustre file system or a GPFS file system, so that each of the disks is getting the right number of I/Os per second. We're seeing nice 1 meg sequential I/Os which are completely aligned with the block size, the RAID chunk size of the file system. And then we pass the benchmark, and the customer congratulates us, give us lots of money, and then the applications are introduced to the system, and we never see this number again, ever. Until about 4 years later, and it's thrown in the bin, and they buy a new one. We go round and round like this forever. So applications really are diverse, and well, here's a little snapshot from a customer of ours. So even a very large national lab in the US can see highly diverse range of I/O sizes. This is just the sizes. Firstly, there's a lot of writes, and secondly, the vast majority of those writes are 4K, 16K, 32K. So these are tiny things. And we do the IOR benchmark, or the acceptance test benchmarks, almost exclusively on 1 meg or something like this. So nowhere near what the actual supercomputer is doing. So I'm going to tell you how we're trying to tackle this, and I have stolen some marketing slides, so they're quite good slides. And then we'll talk about how we might help this community in the next few years. So we've developed this thing, and it's taken about 5 years. We saw this problem a few years ago, and of course there's a few things coming together. So first, there's this demand, because we can see these different applications, GPUs, machine learning, and all these different algorithms coming to play, and they're pressuring the system in different ways. But also there's this other trend of this lovely non-volatile memory, which seems to satisfy all our needs. It's got extremely low latency, the costs are coming down pretty rapidly. We're now able to scale it out to systems of a petabyte, and people don't, die from the budget cost of that. It's not extreme anymore. But we tried to develop a piece of software that allowed you to stretch the capabilities of the NVMe devices, non-volatile memory, solid-state devices, NAND flash, etc. We need to extend that capability right through to the application. And the problem is, if you take these beautiful devices from Intel or Micron or Toshiba or whoever, and you place them down here in the file system, then some things go faster, but many things don't go faster, because we've got this big file system in the way. We've got a software infrastructure between your application, across the network, into the servers, through the SCSI layer, down to our storage controller, and behind that we've placed these non-volatile memory devices. And that's a fundamental problem that we couldn't really overcome without doing something like this. So here what we did is you got some nice shiny boxes with a beautiful bezel on the front, but really it's just software. It's software development. In fact, these are pretty basic systems right here. These aren't the usual sort of DDN high-end hardware devices. These are pretty simple, dumb things, and we've installed the software across them. What we've done there is we've installed a new client on those application nodes. Over there, the compute nodes now run our special IME client. IME, by the way, stands for Infinite Memory Engine. Okay? Marketing guys had a field day. Infinite Memory Engine. So we absorb the I/O directly from the applications, and we pass it into our special system. And I'll tell you how that works soon. And then later on, that gets passed into the backing file system, which could be Lustre or GPFS or pretty much whatever, but today we support those two parallel file systems. So as far as the application is concerned, it's really only talking directly to this new layer that's been introduced in between the application and the backing file system. So that means we now at least have the potential to speed everything up and gain the advantages that these non-volatile memory devices should be able to give us. So it's not just that, it's not just about I/O, it's a flash cache. So you can do this system, you can build a whole file system out of it, all right? But we're particularly interested in developing a flash cache because that allows you to take your budget, take a portion of it, and use that to make stuff go really fast with this IME layer. But you still need a big portion to hold the stuff long term, using traditional parallel file systems, for example. So the cache aspect is quite important, certainly as regards economics, because you don't want to buy a 5 petabyte flash system, that's going to be really expensive. But you could buy a 500 terabyte flash cache on top of an existing file system. So the cache aspect is important. And we happen to know that it works very well in almost all environments. So there's some particular environments where it doesn't work, where a cache just doesn't work because you always, for some reason, want to address the whole 5 petabyte backing file system completely randomly. Those are very, very specific cases. The vast majority of cases like this, we see this complete diverse usage and utilization of the backing file system, such that whilst we spec the file system for, let's say, 40 gigabytes a second, most of the time we're only using a tiny fraction of that. So that picture there gives us the idea that we can certainly present a fast layer to buffer in these IOs. We've got time to push those IOs to the backing file system before the next activity starts filling up this cache. And just to outline that a little bit more, just taking one little use case out of many. So there's lots of use cases, read and write random IO, workflows, shared file, blah, blah, blah. Here's a checkpoint, and we're doing it using a cache. I can't actually walk away from this microphone, but I would do if I could. Here we see, move the microphone. So here you can see a time axis along the bottom, and then over this axis here is the throughput coming from the application. And what we're doing is we've got a sort of Is my volume still good? Great. So we're starting our application over here, and it's exascale, right? So we may be running across 100,000 cores, and one of those is going to die every few minutes or whatever it is, or every few hours. The chances are our compute program is not going to complete before the application is finished, because something's going to die. So we need to checkpoint regularly. And checkpointing to the parallel file system can take a long time. So if we've got a memory size of a couple of terabytes, that can take half an hour or an hour to get down to the parallel file system. We shrink that with a fast cache layer. And if we time things correctly and integrate with the parallel file system nicely, then our compute application starts running. It checkpoints quickly to the parallel file system. There's time, to the cache. And then there's time for that cache to flush back to the file system and free itself up before the next checkpoint. So this is a really constrained example. You've only just bought enough cache to accept your checkpoint. But anyway, there is models which we can do and hints you can give us which allows us to manage that situation. If you buy twice as much cache, then you can avoid this flushing mechanism. Everything's much safer and you can keep checkpoint to the system. So anyway, there's two so this one and this one, two kind of very simple use cases about how we use these caches and why they're kind of relevant. So we built the system. It took us 4 years, 5 years. It's GA now, and it's developed. It's got some nice characteristics I want to talk through. The consequences of those characteristics are things like this. So this is WRF. We ran this literally 2 weeks ago on a large system in Singapore. Thank you very much to A*. So the A* system is quite a large system. It's got a Lustre backing file system, and which is quite large, and an IME cache. And we basically run WRF, and we quilt the I/O. So we're doing parallel I/O, and we compare the Lustre performance with the IME performance. Remember, one of those elements on the table was that Lustre doesn't really like having many, many threads, or no disk-based file system likes having many, many threads because it starts thrashing. We start seeking more than we are doing I/O. And this is kind of the effect we're seeing here when we run this parallel netcdf job with a large WRF I/O problem on top of Lustre. We just see this large I/O time. If we run it on IME, then we shrink that a lot. So this looks great, but how on earth is that working is the question on everybody's lips. Again, this is a bit marketing. Sorry about the flames. I got a bit carried away with the flames. So we got this single shared namespace. So the cache here is presenting a single shared namespace. In fact, the whole backing file system is presented through the cache, totally transparently. And we do that by, when the application does a metadata request or a namespace operation, it actually gets passed through to the file system, which means it just looks like the file system. The mount point you get just looks like nothing has changed, but somehow the I/O gets taken sideways and placed in this very fast cache. And file systems don't really do random writes very well. They don't really do random reads very well. They don't do shared file I/O very well. They don't do high concurrency, high thread counts very well. And those are all the things that IME does well. So we try and tackle these difficult I/O problems. And really the kind of point of the talk is that that's a question to application developers in the room. It's difficult to contort your duck, your application, into the shape that A, fits the GPU, B, fits the GPU to host CPU architecture, also matches up with the network characteristics, and then we come along and say, please can you also align your block size to the file system, make sure you don't do random I/O, don't do shared file I/O, don't do high metadata activity. We add these whole pile of constraints. So what we're trying to do here is allow the algorithms to be free to do the thing they want to do and take the pressure on our side and try and relieve that with this cache layer, which is kind of what we do over here. We've got some lots and lots of graphs on that subject. But the other nice thing is when you build a piece of software from the start, just 4 years ago, using the latest technologies, latest computer science, you get a bunch of other nice stuff happening as well. So I won't bore you with the details, but the applications can choose how well protected they want their data to be, they can either just go super fast with no protection, or they can go a little bit slower but add protection against SSD failures or whatever. And the applications can do that themselves. They can request this on the fly. Oh, rebuilds are very fast. Lots of details there. So how long do you want me to take? Because this could take forever, really.
15 more minutes.
Fine. And please do ask questions. Quite a lot of data in this talk. So I said it's got some pretty fundamental changes internally. And you know, a parallel file system, literally Lustre and GPFS both started out 15, 20 years ago. We started this about 3 or 4 years ago, and the internals kind of are quite different. We have this distributed hash table. That's the equivalent to the metadata system. So we've taken what used to be a metadata system, i.e. a number of servers with essentially a database of inodes, and we replaced that by this distributed hash table. Now, a distributed hash table essentially allows any component within the I/O system to find the owning server for a piece of data without asking it, or without asking anything where it is. You can perform a hash function on the inode, and that will tell you who's got the data and who to ask. So we kind of avoid a lot of metadata problems internally by using this DHT. We have a log-structured file system as well. So we don't use the inode pointers extents file system thing like most file systems do. It's a log-structured file system. A logging structured file system or a log-structured file system is one where all the I/O you get, we're free to just throw it on the end.
Question on this hash function, this distributed hash map. So where is it sitting? Is it sitting in the memory of the IME?
Yes.
Okay. Then how do you populate it? At some point you have to move the metadata.
So let's say an application wants to write to a file, a particular offset, a particular length, particular inode. It will then perform a hash function on that combination of numbers, and that will tell us which server to send the I/O to. It'll go ahead and send the I/O to that server, and then when that server gets the I/O, it'll process it and basically tell everybody else, I've got this data. So now we have it's like a billions of updates per second, and it's very, very linear scaling, as opposed to the limitation we have today with conventional file systems of around 100,000. It's a big change. So it sounds like it could be really cool, right? But I'm going to have to change my application completely and start from scratch and rewrite to some crazy new API you developed. So this is kind of, again, the second sort of big principle about IME is we've tried to maintain POSIX compliance. Also, we support MPI/IO. You saw the NetCDF WARF job. We didn't do application changes there. We do have an API. In fact, we don't really use this at all. All applications use POSIX or MPI/IO. So our system, our client presents a POSIX interface to the applications, and also we have an MPI library that allow MPI/IO applications to relink to this library and use IME. So I'm going to say no application changes. But you saw the quilting example with WARF before. Actually, what we did is we took a WARF application as given to us by a customer, and we unde-optimized it. So it came to us optimized for a parallel file system by reducing the number of threads doing I/O. We undid that to allow more threads, more fire hoses, and that gave us a speed up. So we can kind of undo things application developers had to do to optimize for file systems. We can usually take those away. There's integration with scheduling systems. So there's two sorry, yes.
One question on the previous slide. So I mean that we have to use your MPI library.
Well, you have to use our MPI library. But that means you take OpenMPI or MVAR pitch, you build it against our Romeo version.
Everything in general on Trace T0 machine, typically they're supporting some MPI library. And if you come with an issue with your MPI library, then yeah, you're in trouble with the support, I guess.
Yeah. Oh, we have to support that. But I mean, it's MPitch, it's MVAR pitch or OpenMPI, but we've linked it against our underlying libraries. So it's the same source code, but it's relinked against our libraries. So it's a middleware house. So we don't have to do any integration, in fact. There is some kind of HSM-like features within the cache. So when you throw I/O into it, if you didn't do anything, the IME system would at some point say, I'm getting full, and it's going to start pushing data down to the parallel file system. If you just open a file and it's not in the cache, IME will go, I haven't got that, and transparently to the application, it will go and fetch it from the file system. So all this stuff can happen without any user understanding this cache layer. But we also provide, for more exascale applications or unique applications, we provide these hooks so that you can stage files into the cache, you can purge files out, or you can explicitly flush files down to the parallel file system. So we provide the APIs, the mechanics to be able to push this through manually, but also there are mechanisms built in to allow this data flow to happen automatically in the background. I'm going to get onto application stuff. Here's a couple of sort of performance numbers. So here we have 47 gigabytes a second from a 4U system. So typically with a file system, this is going to take a whole rack. With IME, we put a couple of servers in front of your storage system, and we get a very large speed up. And that's, quite a lot of that's due to the fact we're using SSDs, but we're implementing it as this nice, neat software cache. We're interfacing directly to the applications, and that allows us to take away some of those layers. So the remarkable things tend to be like 4K sequential I/O. We're doing 40 gigabytes a second there. So this is crazy numbers, which you can't really do with a file system. It's very difficult to get these sort of small I/O figures. So this one's actually sequential. In fact, it doesn't matter if you do sequential or random. The random I/O is treated identically to sequential, which is a bit of a long topic. There's a single shared file. So that's the other thing you can do. Today, application developers really need to split their files up, because at some point you'll hit the locking problems within a file. IME really takes away some of these locking problems. Again, it's a bit deep for today, but we can have these many threads talking to a single shared file and do so at very large speed. So the A-star system, which we built in Singapore, we got over a terabyte a second into a single shared file. So again, that's another number that's really remarkable. You couldn't do it with a file system, but you can do it with IME. And again, that gives new potential to application developers to do things a bit differently. So if you want to have one large file which you checkpoint to, read from, with an index area, do random I/O to, that's no problem now. It's a terrible problem with a parallel file system, but it's quite fine with IME. Is that 5 minutes left? Yeah. So there's like half an hour's talk in this couple of slides. So about aligning block boundaries. So we've got an application. It likes to work in certain block sizes. And this is a terrible problem because, if you don't do that, then you get a sort of contention problem when you map the in-memory blocks to the file system blocks. And if you do it badly, then you're going to have contention when you do those writes. The parallel file system is going to start locking, and essentially what you see here is a sequential process for that write process. So we've got a parallel application. It thinks it's doing parallel I/O, but the file system is preventing that because we're crossing these lock boundaries. So that's a classic parallel file system problem. So we take that away with IME. In fact, there's a nice plot of exactly that happening. Multiple threads, and some of them get delayed in time. So some of them are waiting back here for this lock to be freed before they can finally go and start writing into this file. And this slide here, you'll see the same picture here. I didn't really bother adding axes or labels or anything, but over there, you'll see the IME result. So all these blue lines, which are spread out here with the parallel file, so this one's actually GPFS. When we rerun the application on IME, they're all sitting on top of each other. That's that blue line over there. So there's none of this lock contention now with this new layer. One more slide. This one addresses the random I/O. I'm going to take everybody with me with this slide. So what we're saying here is, normally when you do random I/O, essentially you send 4K I/Os into the file system. It's essentially got to process them one at a time. With IME, we've got a very different way of doing things. We can cache all these random I/Os into a big buffer, and then we can transact them all in bulk. And we're able to do that because we've got this logging file system. I'll go back to that. We're not now scattering these 4K blocks across a disk infrastructure. We can just pile them up and then throw them on the end of a log, because we can track all those little elements with our DHT. So these two things interplay very strongly. But that means that this sequential behavior, all you need to notice is that looks the same as that, apart from the different colors. We're taking the random I/O. It's treated identically to sequential I/O. We stack up in a buffer. we send it across the network, and we write it down to SSDs. And this is why we get these sort of extremely high 4K random IOs at 40 gigabytes a second with IME, because we're implementing this log structuring within the file system layer. So, how can we help? So we are an associate member. We have a system at Idris, and we have an intern, Alexandra, in the Paris office working on these things. I am actually I've got a number of titles really, but I'm primarily the IME product manager. And this is a GA product, right? So you can go out and just spend all your money and buy this stuff. That's not really what I'm interested in with this community here. It's a new GA product. So it went GA middle of last year. We're just about to come up to another release 1.1, but it's as sophisticated as a file system. So I think we've done a good job, but there's plenty of optimizations. There's plenty of ways we can tune, plenty of ways we can, well, not really tweak, but fairly fundamentally adapt the software as it grows to manage different I/O patterns and different ways of working very optimally. And it's my sort of primary interest to do this, to understand all these I/O patterns, and not even the I/O patterns today, but the I/O patterns you want to have, or the way you'd like to have your applications to do I/O for the next 5 years, 10 years, 2 decades, because we want this to be at least a 20, 30-year platform. And we have labs, right? So we have a Paris lab, we have interns, we have people who work in engineering and development on this IME product, doing the software development. We can run tests in that benchmarking lab. We can run tests with you on your site. We do a fairly detailed I/O profiling sort of studies of customer applications, which can allow us to really drill down not on, you know, how much I/O did it do, but where did it do I/O, in what form did that I/O take place? Was it shared file? Was it invoking locking? Was it random, etc.? So I'll pause there and let you ask any questions.